All right, so today I'm gonna give you some tips and tricks and a slight review for terpenes. So I'm gonna go through monoterpenes, sesquiterpenes, diterpenes, and just quickly, touch on triterpenes. But really, the point of this is to help you maybe think about how to study these chapters. For me, the terpene section is the most difficult and the most intimidating. If you have the book, I believe the chapter is something about 130 pages, so try not to get overwhelmed by that. There are some patterns and strategies to think about, and so as you go through the lectures or the book, try not to get focused on the fact that there's so many molecules that exist in this class and focus more on how these cyclization events happen, what are the core members of the different cations that form the structures of these classes of terpenes, and then from there, knowing the transformations that they can undergo, the types of alkyl or hydride shifts or oxidations, should allow you to kind of think about how to rationally propose a synthesis, or a biosynthesis in this case, for some of these terpenoid molecules. So we'll start off with monoterpenes, and so just a quick review. For monoterpenes, it's the condensation of DMAPP, which is here, with IPP. So you lose your phosphate group here, and then I'll give it some red. And you'll form this stabilized carbocation. And then IPP will then attack at the tail end of that position. You GPP basically. So you'll deprotonate, reform your two double bonds, and then you'll have GPP. And this is the same way that you'll get FPP, which is the sesquiterpenes as well. So be familiar with the reaction. It could be an easy question that you have to address. So it's just an SN1 style attack on a carbocation. All right, so that gives you GPP, and really the key to looking at these terpenes is folding them. So as you can see here, I have shown GPP in this folded state, and that's the way you're going to see a lot of these molecules. You might see them rotated, but if you can see the general structure of the folded, uncyclized terpene, that actually is really the key to being able to answer a lot of the questions that you might be asked. So just some general stuff from GPP, it is the E isomer, as shown here. And so that means that if you see any product like geraniol where you have replaced your phosphate with a hydroxyl group, shown here, or maybe that can be oxidized to the aldehyde, you'll see this E here, and then you'll know that it came from GPP, because GPP is the E isomer. But GPP actually doesn't, result in the production of a lot of the more difficult monoterpenes. Those are going to be these cyclized guys over here, and we'll get into this in just a second. But that's actually going to be because what happens is GPP can isomerize, so you can lose this OPP. You'll form a cation again, and then in that case you can actually rotate around this bond, and then you can then add OPP back in, either at this one position here, or just the one here, or this two route, I guess is a better way to say it. And that'll give you the two other classes, which is linaloyl PP and neryl PP, so LPP and NPP. And these are actually, because you have transferred them into these different conformations, more likely to undergo cyclization events. It's not that simple, but in general that's the case. And LPP is the preferred substrate for lots of these different synthases that are going to be doing these cyclization events. So once you've rotated about that bonds, you have, in this case, this is the Z form. Then you can actually do some interesting cyclization chemistry. So if you lose that phosphate, this OPP here, you lose it. Then you see that you can actually form some ring structures. So this is going to close up here, and then you'll form the methyl cation or the alpha terpenyl cation. And this is really the core structure for moving to all of the other cations and then to the other monoterpene products. And so I've kind of drawn an overview here, and we'll go through this, but this is just kind of a way to think about studying this more so than giving you the answers that you probably would like to hear. You're going to need to spend some time drawing these out, doing the transformations, and once you've done them quite a few times and you get used to what they look like and how to manipulate them, it's actually not so bad, but once again, I do understand that this is a pretty intimidating section. So all right, so starting from this A route here, so you can imagine you have this double bond, and it can either attack, forming a bond between this carbon and this carbon, or this carbon and this carbon. So in the case of the pineal cation, you attack and you form this four-membered ring. So this is the A route. Right, and the pineal cation is going to lead to pinene, which you guys can go look that up. So, but you'll see the core structure of pinene is based out of the pineal cation. So if you know how to get from a menthol cation to the pineal cation, you can get to pinene or any number of other things that look like pinene. And then the other thing is the finchal cation you can get from the pineal cation, and that's just going to be and this is something that you need to make sure that you understand, a 1,2 methyl shift to get to this. And so the structure changes a little bit. I've marked the carbon here with the blue dot. So once you migrate this over, this methyl group over, and you change the ring structure here, your blue carbon here is now at the top, at least in this representation, and your tail is now over here. So when you're thinking about how these things form, some things you need to think about is there might be rearrangements, and lots of stuff you can do is trying to break bonds and see how that changes the structure, and see if you can walk back to the family progenitor here, in this case the methyl cation. And if you ever want to, this is something I like to do when I study, I make up dumb names or jokes about what these molecules are or how they're related. So if you know pineal cation, pinene, pine trees, finchal cation, finches, those are birds, happen to often sit in trees. So for me, I usually remember this one pretty well. It doesn't always work for other ones. Sometimes you just gotta remember it, but I like to make dumb jokes. It helps me remember things. And you can give them personalities to make you remember them as well. So, all right, so the other way you can go with this, instead of cyclizing from this carbon, you can cyclize from this carbon. So you can attack down here, as I've shown. And this will be actually, well, I guess I should have shown it there. This is the B route. So you can see here. And in this case, you form a 1,4, bicyclic bridge. And this is the Borneal cation. And this Borneal cation can go a 1,2 methyl shift to the isocamphyl cation. I remember the Borneal cation just because it looks like a tent to me, and I know this will actually eventually go to camphor, camper, tent. So once again, you can make up names to remember what these structures look like. Oftentimes funny, goofy ones, or like I said, you can give them a personality, and sometimes it helps you remember too. All right, so the C route, this is another way of making different types. So you can actually form a bond between this position and the cation, and that'll form this interesting three-membered ring here. This makes the carene type. I think it's careening off to the side, so carene, maybe that'll help you. And then the other things you need to think about are basically hydride shifts as well. And so you can do 1,2 and 1,3 hydride shifts. And so one is where you do, you take this proton, I know this is getting really crowded here, I am sorry, but you take this proton here, and then they go here, right? So 1,2 hydride shift, you're going to move that positive charge to this position, and at that point you can cyclize, and then you can make what's called the Thujal cation. I remember the Thujal cation because it sounds intense. Thujal, I don't know, it just makes me think it's intense, like some kind of Nordic warrior or something. And it's this tight three-membered ring, so to me it's really strained, so that makes sense to me. But you can think of whatever you can. This is most of the cations that you'll need for the monoterpenes. So really the monoterpenes are, while they look kind of difficult at first, not the most difficult to get down. I definitely think once you get to the longer terpenes, like the sesquiterpenes, and especially the triterpenes and their modified forms, they're a little bit more difficult. So there's some things that I said you need to know in addition to what I've shown you there. And once again, that's 1, 2, and 1, 3 H and methyl shifts. So these are going to be significant ways to change where the position of your positive charges or how to form different cyclized groups. So make sure that you're aware of them and how they work. Then there's also some important ones. Maybe you're given a molecule that is looking like this, and you'll have to know maybe how to get there. And the way that you can think about that is you have allylic oxidations and allylic isomerizations. Remember, allylic positions are prone to oxidation or deprotonation because they have stabilized intermediates by resonance. So you can look here, I've just shown limonene. So from limonene, do allylic oxidation at this position because it's next to the double bond over here, right? So 2 oxidations will give you the ketone. And then at that point, you can undergo an allylic isomerization. So if you deprotonate this proton, it's going to be resonance stabilized, then you can isomerize to form the alpha-beta unsaturated ketone. That'll actually give you kind of a conjugated pi system, which is more stable. So, but really the key here is knowing that if I have these functional groups, namely these unsaturations, the positions next to them are usually activated for chemistry, and just as the chemist takes advantage of the allylic position in the chemistry lab, nature also takes advantage of the allylic position in enzymes. So that's kind of the basics for your monoterpenes. So definitely practice making these different cations and then playing maybe down route with a few of the cations to see how these oxidations and transformations will change the product, and then hopefully from that point you'll have an intuition for how to propose a biosynthesis for some of these molecules. All right, so that's monoterpenes. Colors on you. We're going to go white here for the background. I did not have the patience to draw all of these, so I stole them from the book. So yes, you too can go to the book and try and reason your way through these things, but I'll do my best to give you the basics from my perspective. All right, so I didn't show the reaction to make FPP, but sesquiterpenes, which is what we're going to talk about here first, are the 15-membered carbon terpenes, and that's going to be 3 isoprene units. And so it's going to be EE in their initial form here, so E. And I've numbered this because this is a way to think about stuff. It's not foolproof, do not rely on this, but it is a way to think if it makes sense, because sometimes if you look at a folded structure and you're trying to figure out what are the isoprene units that form the core, you can do kind of a count around the carbon chain to see if it fits the structure of the linear form. And so I think of this in the terms of numbering the units. And so here was where your phosphate was over here. And so I've numbered it 1, 2, 3, 4, right? And you'll have a 5th carbon up here, but that's not in the main branch, so I'm not currently worried about that. But do know that this methyl branch comes off the 3 position. That's important. All right, so then you have 1, 2, 3, 4, 1, 2, 3, 4, right? So that's 12 carbons total, and then you have your 3 methyl groups pointing off. And so this gives you an idea of, if you count backwards or forwards on a terpene, that you should maybe be able to figure out where these units are. And this is something that's going to be asked of you potentially on the test, right? So I can, oops, I messed that one up. That's my 4 carbon, right? So 1, 2, 3, 4, and then my 5th, and then 1, 2, 3, 4, and then my 5th, right? So the idea is you should be able to have a good idea of what the units are and the final structures of some of these terpenes. All right, so once again, the key to understanding sesquiterpenes is going to be the folding of the uncyclized intermediate. And the idea is that you're going to fold this in a manner that looks like the products it forms so that it's easier to understand the transformations that are occurring. So just like before, you have GPP and kind of an NPP, LPP difference. So I'll just kind of show you that real quick. So you can also take the EE form, deprotonate it, and then you actually rotate that to form another form. So you have the EE farnesyl cation. This is a little cation, but we'll start with the EE farnesyl cation. This is similar to the GPP that you saw from the monoterpenes. So we will just kind of go through this. So there's a couple ways that you can cyclize these, and shown here, and this is a good guide in your book, it shows you the membered ring that it's going to form. So there's two ways to cyclize the farnesyl cation to form these rings, and one is a 10-membered ring and one is an 11-membered ring. And that just depends if you're going to cyclize from this position, which is going to go to the 10, or this position, which is going to go to the 11 position, or go to the 11-membered ring. So we'll start from the top. So this is the germacryl cation. I tend to think that I see it more. That is not in any way a scientific statement, but I don't know. I think I've seen it more. So on his tests and whatnot. So once you have the germacryl cation, there's a couple different things it can do. As you can see, you're going to start to form different other ring structures. So you're going to either form, a 7-5 or a 6-6. All right. So, and it's the same thing. You form the 5 if you cyclize from this position, because then you'll form this one. So 1, 2, 3, 4, 5. And then if you cyclize here, it'll be 1, 2, 3, 4, 5, 6. So then you'll get to these two final products, and you might think, okay, well, maybe I should practice outlining my terpene units, and that would be good. And the idea here is also that if you know how to fold this thing, you'll pretty much immediately know how to determine which way your chain went. But we can think about that real quick. So let me choose a different color. All right, so the first thing you can think about is, okay, I found my tail. That's over here. That's usually a good place to start, your tail. And then you're going to try and think about which way you're going to go. You're going to circle your tail, and then you'll know that, of course, it's going to be, and I'll go ahead and count it, 4, 3, 2, and then you can either go 1 here or a 1 here. And given that we know how to cyclize, it actually is going to go up. But one thing you can do first is when you look at this, you can say, I'm going to break this ring and not consider that bond here. That'll give you basically your 10-membered ring that you started with. And then you can think about it a little bit more clearly. But because I know this 10-membered ring started from the germacryl cation, right? So it started here. I know it goes this up direction. But that really comes from you understanding how the cations are formed and how they're folded so that you can look at something at the end and then immediately know the correct direction to go. But I'll give you some tricks to basically try and make sure you went the right direction, although they're not foolproof. So I will circle. This is my tail. All right, that will mean the next one will be here. So this is going to be the 4, 3, 2, 1, right? So remember I said the 3 position is always going to have the methyl group hanging off. And so that's a good way for you to recognize if you're going the correct way. Because if you end up counting these carbons backwards, and you can do this any way you want, I just do 4, 3, 2, 1 because, and just to reiterate, when I start from the tail, I know that's the 4 position of that isoprene unit, right? So this would be, I know I'm walking backwards, right? So in this case, it's 4, 3, 2, 1. The next one's going to be 4, and then 3. And once again, like I said, you're going to have the methyl group hanging off there. So it's really trying to understand how the linear molecule relates to the cyclic one. And so just to finish this, and once you have that figured out and you know which way you go, you're pretty much done. So you're going to take your methyl group there, 4, 3, 2, 1. And then, just for good measure, this would be your 4, 3, 2, and then it's kind of labeled because of, anyway, it's 4, 3, 2, 1. So then you'll have this guy. All right, so that means all my carbons are accounted for. So that's the other thing you want to make sure after you've done all of your circling. You want to make sure that you didn't leave any carbons out. You might have figured out, aha, I have all of my terpenoids done, but really you missed a very important carbon. If you miss circling a carbon, it's wrong, or it might mean that if you miss circling a carbon, you went the wrong way and didn't realize it, and then finding out that you didn't actually include that carbon means you did the wrong thing, and then you have to start over. But as you can see, really the key is looking at these cation intermediates and how they form structures, right? So you have a 10-membered ring formation, and then what I'm going to do is either form from this 10-membered ring 5-7 or a 6-6. So by just breaking the middle positions here, you can really see the you can go backwards one step, right? So you can end up back basically to this position, and that will help you, or I guess this position, I have it, there we go. So that'll help you try to understand where you came from, and especially if you know that this is, from the germacryl cation, you can immediately identify your tail, you'll know how it's folded. And so we'll quickly run through this one. So if you break that ring, it's the same direction as the last one. You're going to go here. So 4, 3, 2, oh, hang on. 3, 2, 1. 4, 3, 2, 1, and then we'll get these last 4 over here. 4, 3, 2, 1. All right, the other way that this guy can go is the 11-membered ring, and that is going to make the humulil cation. It just looks funky to me. It's humulil. It's going to make compounds that are found in hops, like humulone, and it can make a different cation called the caryophylyl cation as well. And I don't know. I just think it looks like a big H, so I think it's humulil. I don't know. I try to do stuff to remember stuff. Hopefully that will help out. But so that's it for the EE farnesyl cation. So like before, you have a greater number of structures you can form by isomerizing around this double bond and going from the EE form to the EZ form. And so that's shown here, the EZ farnesyl cation. And the thing to note is that you're actually changing the way that you fold this, right? So starting from here, you can see that, I have folded it so that this guy's hanging off in the corner. This one's down, and I have my methyl group from this position right at the center, right? So you see that let's see, I'm going to erase stuff to make this a little clear. Now, oftentimes, if I form these bicyclic systems, I have this methyl group kind of at the middle. It only really works for the eudesmal cation, but it can be useful. But you can see it is going to change the arrangement of the methyl group and the tail around the ring, whereas before the tail is over here and the methyl group is here. Now it's here and here. So just some things to consider. All right, so we've refolded it, so it's going to change the general structure, but the same concepts are the same. But in this case, you have different cyclization fates. So instead of just go ahead and then forming your 10-membered ring, you can actually form a 6-membered ring first, and that's going to give you the bisabolyl cation. I don't know if I'm pronouncing that right, but that's what I call it. And then you can see that you're going to go from there. This is your 6-membered ring, and then you're going to form a 6-6. So this is actually the this is the amorphal cation. It's somewhat related in structure to the eudesmal cation, which you can see here. But just note that they are different, although they look the same. And if you can recognize the methyl pattern coming off of these bicyclic systems, then you can start to understand more quickly where a natural product comes from, at least in regards to its cation. All right, so there's other ways you can form a 7-membered ring as well. So it's also the same concept. If I cyclize from this position or this position, I'll form either the 6 or the 7-membered ring. And then the next step is this formation of the carotyl cation. If you say that incorrectly to people, you can blame me. That's fine. All right, so this one's a little difficult though. So if you were just to look at it, you might not know exactly what's going on. So just as a rule of thumb, if you want to figure out how things are cyclized and you're confused by this transformation, just number your carbons and follow the carbons, and this way you can see where things are. If I start from here, this is 1, 2, 3, 4, 5, 6, 7, and I know the 7 position is where I'm forming this bond. That means I'm going to have 1, 2, 3, 4, 5, 6, 7. And that helps me understand basically the route that I'm taking here, right? So the 3 position has the methyl group. That makes sense to me. That's good. And so really I'm making a weird route of folding this this terpene. All right, so if we take this structure over here and we go to the carottyl cation, we can think about how this might cyclize. So this one's a little bit tricky, and so you might think that you would break this bond first, and if you did do that, you would realize that if you were to walk around this and say 4, 3, 2, 1, all right, that's fine. Then you'd think, okay, 4, 3, 2, 1, and you'll have a methyl position at the 4 here. And so you can't go that way, which means that breaking this bond isn't the right one to break, more than likely. So, but if I know how this thing is cyclized, I'll actually realize that this bond actually is right here, is actually going to give me the ability to let this disconnect, because this is the bond I form here. And then I can actually snake in through the structure. So I'll show you what it looks like. 4, 3, 2, 1, 4, 3, 2, 1, 4, 3, 2, 1. And in that case, you'll find that you have your terpene units. All right, 4. Go up this way, and then come back around. So of the monoterpenes and the sesquiterpenes, of the sesquiterpenes that we see here, I would say that the formation of the carottyl cation is one of the more difficult ones, but once again, by knowing how things are folded and formed, it's a little bit easier for you to identify what the terpene units are. So nothing's really going to substitute being able to look at these different cations and their folded structures and being able to walk through how they would form using some reasoning and logic. All right, so let's look at some real-world problems. So I've got 2 shown for you here, matricin and artemisinin. Artemisinin is a favorite of Mike, and I think I've seen a matricin-like molecule in one of the practice exams or in one of the practice problems, so we'll go over those. So looking at this, you can see that there's different decorations, and those are meant to confuse you. No, that's not really the case, but they are going to, and it's good to be able to pick out what kind of modifications happen so that you can find the core structure of your terpene. So looking at this, you might not be able to find a tail immediately, but I can tell you that it's right here. This is going to be your tail, and you can see you had an oxidation back here at this terminal carbon, which maybe went to the carboxylic acid, which then allowed this lactone to form, right? So you could cut there, right? If you cut there and get rid of this lactone, then you really see that you have what would be the makings of a tail. And given what we know about the different ways that these can cyclize, then you can think about how to go around this thing. So for me, once I have the tail, I realize that I can just kind of continue as I did before, going up to the right. This is going to be 4, 3, 2, 1, and then once again 4, 3, 2, 1, and then 4, 3, 2, 1. And I can circle them as such. Alrighty. So I looked in the book for this one, and I believe this one comes from the eudesmal cation. I am going to double check before I lie to you. All right, well, it comes from the germacryl cation. You can find the basic formation of this is parthenolides, kind of the other core form of this, and you're going to find it on page 214 of the book. So yeah, so there's a ring rearrangement that occurs at some point to give you this 5, 7 versus the 6, 6. All right, so then going down, This is artemisinin. Artemisinin is another challenging one because once again you have all of these oxygens all over the place. You've ruined what would be your familiar structure, and so you have to figure out where it came from. And so artemisinin, once again we can look at this and say let's cut some things that look like they weren't there to begin with. So the core terpene structure does not have a lactone. It doesn't have these oxygen bridges, right? But the one you're going to find difficult is here, and this is actually an oxygen that's inserted in between a double bond at some point during the biosynthesis of artemisinin, which you should probably review. It's a very famous molecule. It's a Nobel Prize winner, so Mike tends to bring questions up on this one. I don't know if you'll get one this year, but whether or not it's on the test, it's still a fun one to know because it's really an important molecule. All right, so once again, you can see that this is your tail. And from what we know about this, we can see this looks like it was probably a 6-6 ring structure. I could probably cut there in the middle. And from my understanding of sesquiterpenes and how they fold, because I'm aware of the different cations, I would imagine that I'm going to go up and to the right. Because to me, this looks a lot like this guy over here, the amorphal cation. You can see this methyl group here. You can see, these methyl groups down here. They seem to match the amorphal cation. And so I can say this is 4, 3, 2, 1, 4, 3, 2, 1. So I'll go ahead and outline that. Let's erase this. I don't know what that's doing there. What's it go for? Supposed to be squigglies. All right. Then 4, 3, and then oh no, there's an oxygen in the way. But don't worry, like I said, it was inserted. So 2 and then 1, right? So then that means this is going to make up the rest of your terpene unit. So as you can see, it's really understanding the cation that can help you understand how to go around these circles. But once again, there are tricks you can do, like numbering these carbons and making sure that the backbone that you follow fits the same pattern as the linear or the pre-cyclized form of the terpene. Alrighty, cool. So I put together an answer to one of the questions on the practice problems. I think this is Chapter 5 practice problems is the name on the Canvas page. And this is the synthesis of cubene. So cubene is shown here. I don't know, cubene, for some reason it looks like a cubene to me. I don't know, some people look like what they're named. Cubene looks like cubene to me. Anyway, so cubene is a sesquiterpene. And looking at this, the question says, how do you go from FPP over to cubene and propose a rational route mechanistically? And so looking at cubene, I can see that it fits, the kind of pattern of these six different ring cations that we just talked about. And you can see that, and maybe Mike did this on purpose, the way that it's represented is flipped, right? So typically this group is over here, right? So, but with that in mind, you can see that if I was to guess, looking at this now, this comes from either the amorphal cation or the cadenyl cation, as the eudesmal cation has a different decoration pattern around its ring structure. But regardless, you can go through and try to form this and fold this, and since this is drawn in a different way, you might have to think about how to fold it in a different way. But the first step in this is actually going to be knowing that you're going to go from FPP, and FPP, you're going to actually kick out this OPP, and then you're going to form the resonance disabled cation, which then can rotate around this bond, and then you're going to go to the neural form of this. So then it's a neural cation. Let's see what it's called before I lie to you. So the neurolittle, that's what it is, neurolittle, or the EZ farnesyl cation. So we're going to form E, and then it's going to become the Z form. All right, so I'm going to fold this up just like it looks in the structure. You can see that I have folded it very similarly to the way it looks here. And this is just the same thing that's done in the book. It's reverse. It's kind of just flopped 180 degrees. So the first thing is forming this this 10-membered ring here, right? And then you'll have a new bond there. And then you'll have to figure out a way to cyclize and form the central bond here. So if I form this 10-membered ring first, then my cation is going to be here, which means I'm going to have to do a 1,3 hydride shift to move my cation to this position. And then by doing so, I set up the ring to cyclize to form my 6,6 system, right? So at this point, you can have these guys come in and attack this positive charge and form your 6,6 ring system. And then once you have that, you're getting real close, and then you'll realize if you went this route, you actually made the cadenyl cation shown here. It's just flipped 180 degrees. And if you try making this, you can maybe go through the amorphal cation and do a number of H shifts or other things, but this is, from what I found, the most direct route. All right, so once you have the 6,6 system, you know you have to form this this really strained three-membered ring here. And so in order to do that, you need to shift your positive charge, and you can easily do that. And I wrote 1,3, but it looks like it's a 1,2 shift. Sorry about that. So shifting that hydrogen over will give you the positive charge at the bridging position, allowing you to form your bond between the double bond and the bridging position, thereby making your three-membered ring. And the only thing that's left to do is to form the double bond on the side of this ring, and since you have broken this double bond here, you're going to form the cation at this position so you can see it, and then just, you know, a classic E1 style elimination of this proton will give you the double bond there and give you your final product cubene, which once again I said really comes from going the cadenyl cation route. Alright, so that's a way to kind of put all that together and think about stuff. So I guess got one more thing for you, and it's thinking about the diterpenes and triterpenes. So I just have two to show you, and one's taxodiene. It's a favorite, given that Taxol is a very important anti-cancer drug. So I'll go over this top part in a second, but taxodiene is shown here. And if you wanted to figure out how to outline the backbone of taxodiene, you would need to start with the tail. And there's two ways to think about that. You can cut from the top or the bottom. So if you cut from the top, you actually get to the right answer pretty quickly. So you will have your tail, and then you'll come around. So this is going to be 4, 3, 2, 1. And then you'll have the next one is 4, 3, 2. Oop, that's not a 2. That's a 1. That was right. 2, 1, 4, 3, 2, 1, 4, 3, 2, 1. And now I have gotten all my backbone carbon. I'll go ahead and outline them, and then technically we would be done with this. Alrighty, so we can play with this the other way, and this I haven't really practiced, so we'll see if this works out, but if you chop it the other way, you'll have it hanging off the end here, and then you'll see that this doesn't look as good. It doesn't look like something that you'll see. 4, 3, 2, 1. That's kind of strange. So given the connection here is really awkward, this isn't something that you're going to see in a normal tail-to-tail or head-to-tail style thing. Maybe that's not correct, but who knows? It could be. So maybe we think about the other way. 4, 3, 2, 1. Okay, well that's okay. And then 4, 3, 2, 1. That's okay. 4, 3, 2, 1. Okay, and then you'll see when you get here, 4, 3, 2, 1, but you're missing your methyl group. So either way you slice it, if you chop this the wrong direction and you try to count your carbon backbones, you'll find that it doesn't really work that well. So that's kind of a way to think about trying to go through it if you don't know, but really the easier way is to look at how this is made initially. I would definitely be familiar with the general route through to taxidiene. Like I said, very important drug. And so you can see that you fold this up in this manner, and the first thing you're going to do is form this big ring here. So if you know that you're going to form this ring in this position, you already know that no matter what, if you have this, you're going to have to start and go left around this ring. And then the second thing you're going to do is form this bridged dimethyl group here. And once again, this is the one that we cut and then went around this way, and that gave us the correct answer. And then you'll see that you have further modifications from there to get to the structure. You form this other ring system back here last. This six-membered ring is formed here, right? So you could also have initially just cut there as well. So this one's kind of nice because you can think about it and take some time to maybe go through the different routes and you can figure it out. But the easiest way to understand these is to have a good idea of how to fold the structures, because you practice some of the problems, and then from there being able to walk back about how it cyclizes. So another one is this copalyl intermediate here, and that's also formed from GGPP. And this is really when you're going to start seeing this interesting kind of zigzag folding, and this is pretty common of the longer terpenes, especially the triterpenes. And then you end up with these, six-membered or 665 or membered systems, right? So you'll see here over in steviol, you can see it. So you should be able to walk this back, because if you understand that this is folded in kind of a snake pattern, you'll have to snake through the structure in order to get it. So here's your tail. And I know if I'm going to snake around, I have to go up this way, right? So 4, 3, it's not 3. It's a different color. 4, 3, 2, 1, 4, 3, 2, 1. Methyl groups right there, looking good. 4, 3, 2, 1. Methyl group is there, looking good. 4, 3, 2, 1. So I've been able to kind of snake around this. It's getting kind of ugly, but just bear with me. And then 4, 3, 2. All right, so you can see I've been able to circle all of my represented terpenes. All right, so we'll go through one of the real world problems for this one. This is steviol, so it's from the stevia plant, the one that gives you your calorie-free sugars. And we'll walk around this. This is from copalyl, so you can kind of see where things come from. So once again, this is your tail. It's been oxidized, so go ahead and outline it. All right, so cool. So we'll walk that way. Let's go ahead and number some stuff. 4, 3, 2, 1. 4, 3, 2, 1. Here's your methyl group. 4, 3, 2, 1. There's your methyl group. And then 4, 3, 2, 1. And then there's your methyl group. All right, so let's go ahead and circle her up. Oops. Anyway, do be careful when you circle stuff on the test so that I can follow what you circled. Do a better job than I just did. It's a little hard on this bamboo pad. Alright, so the last thing we're going to talk about is triterpenes. So triterpenes are C30s, and just want to reiterate how they're made. It's 2 FPP molecules, and instead of being put together head to tail. It's a tail to tail kind of style. You can see here there's a difference in what you would expect if you had continued to add IPPs to the back end of your growing terpene. So this means that you can't really try to think about counting backwards from the tail as easily. So before I was saying, okay, well, I try to think of the linear numbering and seeing if, the pattern on the ring that I'm dealing with or the product matches, barring that there haven't been any methyl shifts that will ruin it. But before it was 4, 3, 2, 1, and your 3 position has this methyl group. You can see that it's going to be okay because the first guy here is made from an FPP. We'll do it one more time. 4, 3, 2, 1. Your 3 position there. But now you're going to see that it's actually going to shift because it was like a tail-to-tail connection here. So in this case, it's going to be 4, 3, 2, 1, and then it switches, and you have it at the 2 position. And this is going to get a little more complex in a second. You'll see. But once again, to the 2 position, 4, 3, 2, 1. So it gets a little more confusing with triterpenes. You kind of use this kind of approach. So like I said, be careful. Really, the best way to know how to do this is to have played with, the starting structures and cyclized them and drawn them and done the different shifts that will make the steroid. Definitely need to know how to do, the basic steroids like lanosterol shown here. So if we have a triterpene and we fold it, you can see that it folds very similar to what we were just seeing for these diterpenes. So you have this, well, not all diterpenes, but some. You have this nice snaking pattern, and this is really just drawing it so you can see the rings that will form during this cascade that closes this up, which generally looks like this. All right. So that's going to get you to the protosterol cation. And the reason I'm showing you this is because you should, and if you feel kind of intimidated by it, don't. You should just try this a couple times because who knows, this would be a good question to ask, and there are some rearrangements here. So when you're looking at, this final product, lanosterol, and this is the protosterol cation root to lanosterol, you have to recognize that some of these methyl positions have moved, and that might actually be a good question you could be asked. So you can see here that you have this cascade of hydride and methyl shifts, right? So you're going to form a double bond there. This methyl group's going to move. This one's going to move over here. This proton's going to jump, and then voila. And that process is going to give you lanosterol. So I show this because if you need to go through and find the backbone of lanosterol, it's good to know how things have moved because you're now going to be dealing with, especially this position, being in a spot that you don't expect, and this one also is going to have a methyl group that you wouldn't expect. So if you're going around trying to figure out what the terpene backbone is that created this, you might actually have an issue with that position, and this is kind of how you would figure that out. So you can see here, just like before, it's going to snake. And really, that's what makes it nice and easy, is that, if that's the case, then you can really think about how to do this starting from the tail without too much thought. So let's go ahead and start to outline stuff. So you'll have your tail. All right, and then here. So we're going to snake back in. And so far it fits the general trend. This is a 4, 3, 2, 1, 4, 3, 2, 1. So it's going to change though, so I would be very careful with this, just because, yeah, you're going to see it right now. So if I am going to come, I know it's going to go this way. So 4, 3, 2, 1 is over here. As you notice, I'm missing a methyl group, and as I showed you here, the methyl group that was right here is now moved over, and that was here and is now there. So really, I would have to come in and circle this guy to find my other methyl group for my terpene unit. And then you'll see here, 4, 3, 2, 1. Don't let this fool you. This was actually here before, right? So it would be 4, 3, 2. And so just like I showed you over there, your pattern is going to change after the first 15. So after you're done with the first FPP, it's going to switch. So now you have it at the 2 position. But once again, due to methyl shifts, it makes it a little difficult to discern that. So it's 4, 3, 2, 1. So grab this guy. All right, 4, 3, 2, 1. You can see it right there. There's your little Y shape. And then 4, 3, 2, 1. All right, so that's triterpenes. Definitely try to know how to do the basics of moving around when it comes to the steroids. So you need to know cycloartenol and linosterol. Both of those, I would say, are fair game, and it's really just kind of drawing this protosterol cation and moving some stuff around, and then seeing what's formed. Maybe even numbering the ring if you're feeling ambitious. But other than that, if you know how to fold it, you know how these things move, you can pretty easily find all of the different isoprenode units that make up the structure. All right, with that, thanks for your attention. I will see you guys on Saturday, and yeah, good luck studying.